Factoring is hard. The quadratic sieve, Colin Metcalf, that is me. So, factoring is actually very difficult to do, either by hand or have a computer do it. We don't put a lot of thought into it because it is that thing we did in grade school. It was the opposite of the multiplication table, and we kind of left it as that. But factoring numbers can actually be incredibly difficult, especially as they get larger and larger. Cool math. So the largest number in 1994 that had ever been factored was a 129 decimal digit. That was RSA 129. It was broken using the quadratic sieve, which we'll take a look at in a moment. 1,600 machines were involved to break this large number. In 2009, and this is the current record for the largest number to be broken, RSA 768 was factored. That's 232 decimal digits because 768 refers to the number of bits in the RSA modulus, and it used about 2,000 years of computational power to crack it. Factoring a 1024-bit RSA modulus, which has not been done yet, is about 1,000 times harder than RSA 768. So, yeah, we're looking at then 20,000 years of computational power to crack RSA 1024. Here are some complexities to kind of give you an idea of how difficult it can be to factor large numbers. So we'll say our RSA modulus is n. That means the number of bits, of course, is log 2 of n. So if we wanted to brute force it, we're just trying to find any I that can factor into n, and ideally, because we're looking at an RSA modulus, we're not even looking for just any I that factors into it. We're looking specifically for prime numbers that factor into it. So, for I in range of 2 to the square root of n, note we only have to go to the square root of n because we just need to find one factor that's lower than it. The other one can be larger than the square root, but both can't be larger than the square root. If is a factor I of n, then return I. We found our factor. Easy peasy. But that means we need to go through this square root of n times. There's square root of n steps. But again, b is the log 2 of n. So we're actually looking at an exponentially complex system here with the complexity big O 2 to the b over 2. Now, if you kind of think back to your complexities and your data structures and those sort of things, your sorting algorithms, you may remember that exponentially complex things are not good. It's what we want to avoid. We like polynomial complexities, but unfortunately, when it comes to factoring, we don't have that. The best known factoring algorithm is the general number field sieve. Fastest for factoring numbers larger than 100 decimal digits or so. It still has a exponential complexity, and you can see it there. It's big O of b to the 1/3 times log b to the 2/3. Still exponentially complex. So that's the best we've got, and we are not even close to approaching a polynomial runtime. Why is factoring so hard, and why does it matter, though? Probably what a lot of people are thinking of. Why is a kind of a forgotten part of math, or I shouldn't say forgotten, but forgotten by the majority of people who may not be really math nerds. Why does it matter so much? Many modern encryption methods use large primes in their cryptographic systems. RSA is a good example of that. Its entire basis is on prime numbers. Computers are very good at multiplying large primes together. It makes it very good for encryption. You can encrypt things. When you want to encrypt things, you want to do it quickly, so putting large primes together quickly is good. Computers are very, very bad at factoring large numbers into primes. Incredibly bad. Also good for encryption. It takes too much time. But before we get there, why is it hard? Let's kind of just take a step back and think about it. What are the prime factors of 77? Now, I think most people would jump right away to going 7 times 11. 7 and 11. Prime factors right there. Now, how did we get to there, though? You can look at it. You use your intuition. You may just know that off the top of your head. And those are all valid ways to figure it out. But intuition is not how computers think. You can't make a computer intuitively know something. It doesn't get that concept. And computers are deterministic. They are just kind of A to B. They need to be told what to do. So we can do it that way, brute force it, 77 divided by 2. No. 77 divided by 3. More garbage. 77 divided by 5. More garbage. 77 divided by 7. Bingo, we got it. And then 11 is also a prime. We found our factors. We did it. That's easy when we're dealing with 2 decimal digits, but if we want to deal with, say, RSA 129, it's 129 decimal digits, no person on the planet would want to go through that one at a time, going up each and every prime. In fact, no person on the planet could do it. They'd be dead before they finished. Same with a computer. A computer would take far too long to factor that. So how does this relate to RSA? Again, it's the difficulty of factorization. RSA's entire security is based that it takes too long to factor. It is computationally secure. It requires so much power to crack their RSA modulus into its 2 primes that it is infeasible to even attempt it. That any threats along this vector are considered benign. However, that does mean that you can, in theory, crack any RSA certificate given enough time and computational power. Hence, why RSA's certificates are required to be replaced every 2 to 4 years. And now the quadratic sieve. And so this is kind of be the meat of this presentation right now and what's involved here. So why am I bringing it up? Well, the quadratic sieve, I think this will be a good example to show how hard and time-consuming factoring currently is for our computers, how complex the math of factoring is, and how a lot of this math is actually guesswork. So a lot of people think of math as being very, very straightforward. You plug in the numbers, you get an answer. But when it comes to factoring, there is so much guessing going on and just kind of iterating and just trying new things, trial and error. It's kind of incredible. So background on the quadratic sieve, invented in 1981 by Carl Pomerantz. He's an American number theorist. He received his PhD from Harvard, 72, etc., etc. And here's some general info on it. So this is an L notation, not big O notation, but it would require ln 1/2 steps. So basically a little bit slower than the number field sieve, a little bit faster than brute force. Still exponentially complex, though. It is the fastest sieve for numbers between 40 and 100 digits long, and then second fastest for anything over 100 digits, of course first being the general number-filled sieve. Fermat's factorization method. Before we get into the quadratic sieve itself, I want to talk about Fermat real quick. He is kind of the backbone of the quadratic sieve. So some of us may have seen this before, but for any large number n that we wish to factor, we can set it up as n equals a squared plus a squared minus b squared, which of course can be broken into a minus b times a plus b. These two numbers give us our factors. So n would of course then, a factor of n would of course be the GCD of a plus minus b and n. Fermat's theorems alone is not what's going to get us here, though. So we are going to kind of add a little bit to it. So we're also looking for a and b where a does not equal b, of course, and where a squared is congruent to b squared mod n. Now again, iteration would be terribly painful. We want to avoid iteration, so we're going to create, there's lots of air quotes no one can see, but we're going to create our a and b. We're going to do that by smoothness boundaries. So say the number we wish to factor is 63,787. That does have 2 prime factors, and we'd like to figure out what those are. And that can be very difficult to do if we want to iterate through them one by one, so we're going to try and avoid that using a few clever tricks of the quadratic sieve. And so let's say we choose b as 17, so we're looking at 17 smooth numbers, and this is where we get some more guesswork. Now, I've narrowed us down to 6, but the guesswork would come in finding these 6 to kind of figure out what our factors are going to be. So let's narrow it down here just to 439 squared to 449 squared. And we're going to take all the 17 smooth numbers between those two. So we end up with 439, 441, 444, 445, 447, 449 all squared. And then we can then see the equivalence, or what it's congruent to mod 63787, in a 17 smooth environment. So we get 2 to the 4 times 5 times 17 is congruent to 439 squared mod 63787. Continuing, what do we do with this? Well, we're looking for an a and a b. So we've got our a's somewhat. We have some squares on the left-hand side, but we want to prove that things are perfect squares on the right-hand side as well. And we're going to do that with some linear algebra, actually. So we can put out our sections instead of being in our standard congruence forms. We're going to actually kind of make a little coefficient matrix in a moment. So we have our number of 2s, 3s, 5s, 7s, 11s, so on and so forth. But this is real messy. It's hard to read. We got ugly numbers like 11. We don't want those in there. Let's get rid of it. We don't want 11s. So we're going to actually take everything in mod 2. Now, why can we get away with doing that? Well, we're only looking for perfect squares right now. So because we're only looking for perfect squares, we don't care whether it's 3, 8, 11. We only need to know if it's a 0 or if it's a 1. So, modding everything too, we end up with a very nice system of equations. We get 0 is congruent to x plus x, or x4 plus x6, x2, so on and so forth. Much, much, much easier to read. Now, what do we do with the systems of equations? We can do a few different things. We can use some linear algebra, which I did not type out because it'd be a lot, to make a coefficient matrix of these numbers. So it'd be like 0, 0, 0, 1, 0, 1 for each row, and then we can do some row reduction to allow us to get to this point. Note that if you didn't want to do that, you can go by hand and try and isolate variables, but that's not the easiest way to do things, so instead this worked out a lot better. From here, this is quite solvable. x5 is congruent to 0, so we can plug a 0 into here, as we see up here. Now, we need to figure out what x4 and x6 are. We need to be a little careful, though, because say if we say x4 is 0, that means x6 has to be 0, so we end up with zeros here. So x4, x5, x6 are 0, x3 is a 0, 0, 0, x2 is a 0, that's a 0, x1 0. We've zeroed everything out. We're back to square one. We've proven nothing. So we make a decision. Again, we are now having to do something that is not straightforward. We're doing decision making again in our factoring. That's always going to be difficult for a computer to do. But we make a decision. x4 cannot be 0. It has to be 1. We can continue plugging things in. We'll end up with x6 equaling 1. x3, x2 are both going to have to be 0. And of course, then x1 would be 1. This actually shows us what factors we want to use to form our perfect square. So if we remember back to here, we now have our first, our fourth, and our sixth factors. Well, we can do a little bit of movie magic and some multiplication here. We're going to combine some terms. So we've got 439 squared, 445 squared, and 449 squared congruent to its our 17 smooth boundaries we had earlier. And through some simplification, we get down to this level. And note, square, square, we have two perfect squares on both the left and the right side. We have found our a and our b. So if we think back a little bit, a squared congruent to b squared modulo n was our goal. That is how we're going to find these prime factors of 63,787. Simplifying further, we end up with 7,270 and 49,492, our A and our B. Simple method now, find the greatest common denominator, or the greatest common divisor of 49,492 minus 7,270, and of course 63,787, what we wish to factor, and we'll get 227. That is a prime number. How do we find the other one? Oh, we can just divide. So 63,787 divided by 227, we end up at 281. And there it is. We have successfully broken RSA. I guess this would be 5 for our 5 decimal digits. Now, note how much guesswork I kind of left out here. We skipped a good bit. So we skipped the part of where we'd have to go and find each of these 439, 441, 444. We have to find and prove those are 17 smooth. We'd have to find not only that those individual ones are 17 smooth, but all the other primes up to there we may have had to look at. Now a computer gets a little bit of an advantage in some areas. Instead of 17 smooth, it can do a much larger number. It can do much larger prime smoothness because it can calculate that faster. I'm only human, so I can't do that. I need to keep things small for my tiny mammal brain. But I also have the advantage, being human, of making some intuition decisions that a computer would have to calculate and crunch both sides of. Alright, and then just kind of an example of a quadratic siev's full potential, because we saw it do it with a 5 decimal number. It did it with the, again, 129 decimal digits. It used 1,600 computers, 600 volunteers from around the internet, and that was in '94. And they won $100, which I think is probably not a little bit cheap, but $100 is $100. And this is RSA 129. If you really want to get a grasp of it, this is all one number, all the way down, 129 digits. This numbers this large start to lose meaning for us because we can't grasp the size of that. It just looks like a string of random numbers, right, that mean nothing. But this all is the coprime of these two massive prime numbers. This is what they broke up. This is what broke RSA 129. Was the factoring for these two numbers. And so, yeah, that's going to kind of conclude it then for the quadratic sieve and factoring. I hope that this kind of shows some of the thought process and how much guesswork goes behind factoring, but also shows how much growth there is in the upcoming years and get people excited about cryptography and excited about these kind of obscure math branches. Quantum computers has been a hot topic button recently. Lots of people are wanting to talk about that. Well, factoring in a quantum computer is polynomial exercise. You can use Shor's algorithm. That's big O b cubed. There's polynomial. But until we get there, we're dealing with stuff like this, where it's all exponential, and there's so much more room to go forward and try and figure out how we can get these factorization times down. And for people looking at this currently, I'm sure at some point in the near future, someone will come up with a new algorithm that's slightly faster to the point we're going to need to actually look at systems that aren't only computationally secure off factoring. Here are some references and things like that if you want to check any of that out. Alright, thank you very much. I'm Colin. Bye-bye.